So today we have what I would consider one of our big think episodes, and it'll be clear once we start with our discussion. Here today with Jennifer Prendki, who most recently uh, was at DeepMind, but previous to that was at Atlassian and Figure Eight. And in all three places, she's led data science and data engineering teams. So Jennifer, welcome to the podcast.
Hi, very nice to be here. Thanks for having me, Ben.
And her tagline on her LinkedIn profile is Bridging AI, Data, and Quantum. And you can see from that tagline what we'll be discussing today. So I guess by way of background, Jennifer, so you and I are in data science and data engineering. You have a PhD in the quantum physics area, so you're well versed in quantum computing and following what's going on there. But a lot of our listeners, frankly, aren't, right? So a lot of our listeners probably just read headlines. Some may read articles, even fewer read papers, right? So yeah, so I think that for some people, frankly, quantum computing might be, I don't know, 10 to 15 years away. So maybe give us a very quick overview of where we are today. So what is science fiction and what is realistic today?
Yeah. No, I'm very glad you would ask me this question. So just like for my back. No, so thanks for asking the question. Like it's an interesting one for sure. So you mentioned like I did my PhD in quantum physics. So my story was of course I was doing research on discovering like tiny particles and I thought this was going to be my life from the beginning, right? I mean, I was very passionate about that topic and as I was doing my PhD, like I realized that, of course, I'm using a lot of statistical methods, and I actually fell in love with the problem of like creating data for other people to do research as well, which is how I landed in data science, right? I mean, basically, like I graduated at the time when the recession started, so I like felt like there was a stronger opportunity for somebody like me to have an impact, right? And so as you know, like basically we faced like all of these challenges as data scientists to make data functional for organizations and make it usable, make it like a something that's like intuitive and meaningful for organizations. So I faced like all of the problems that I think you and all of our listeners and viewers today like will know about, right? But I mean, I've always been like very close to what's going on here, and so when you say like quantum, like our useful quantum computers might still be like 10 or 15 years away, like I don't computers for AI as we think about it today might still be like a few years away, right? But when I look at what's happening on the market today, like it's clearly like there are real applications in the quantum computer space today for machine learning applications. So let me maybe explain a little bit more. So the problem with quantum computers is that they're extremely good, or they are getting extremely good at fast inferencing, right? I mean, so basically they're not there yet in terms of training large models. There are like lots of like challenges, like in terms of data management that we can discuss later. But I think we're already seeing like the tip of the iceberg, where there are applications for security in particular, for finance and spaces where the model is not necessarily that complicated, but you need to make a lot of predictions in a short amount of time. So I'm pretty hopeful that this will become increasingly important in industry in the near future. But I'm also very concerned about the fact that there aren't a lot of people bridging both
Is
topics, right? I mean,
So, Jennifer, so the examples you just listed out, are they in the lab? Are they papers? Are they prototypes? So, what's the exact status?
yeah. No, so fair question. So like there are a few like top companies like in the quantum computing space, right? I mean, so I will quote like companies like IonQ or D-Wave or Rigetti, right? I mean, basically like which are all public companies, right? And so they are not working necessarily with your typical organization, but they do have use cases with governmental agencies like NASA, for example, right? I mean, so basically like you could say it's in the lab. Not quite. I think there are like tangible applications that are emerging, but you're pointing out like the exact like challenge, which is basically like going from pure research settings to production, right? I mean, and so basically like one of like that's exactly where I see the problem arising, right? I mean, so basically like and maybe to like it's
So,
like a
so for those of us who are not in this area,
Mhm.
so you named some startups that I've heard of, but frankly, the headlines that most of us read are from the big companies, right? So
Yeah.
Google,
Yep.
IBM, uh, Intel, those kinds of things.
hmm
So are those companies doing anything in terms of the types of applications you're doing, or
Yeah.
they're focused on basic research?
Yeah. No, so I mean, we can quote like recently. I think like the main headlines has been like the Willow computer from Google Quantum, right? I mean, basically like with like cutting edge like performance for quantum supremacy, right? I mean, so quantum supremacy like refers to like things that are feasible only with quantum computers, right? I mean, basically people usually believe that quantum computers bring on full speed, but they actually like help solve problems which are completely intractable with machine learning, right? I mean, our regular machine learning infrastructure, right? And so, of course, you need those computers to be ready in order to be usable, right? I mean, so one of the key problems with quantum computers is that they are storing information and processing information through what we call qubits, right? I mean, so qubits are the quantum equivalent to bits in regular computers, right? And what's special about them is basically they don't just store zero or ones; they store like any value in between. In fact, they can store like complex values, right? I mean, so basically like you have like substantially more information that can be stored into them, right? But the problem is like they're extremely like fragile, sensitive, basically like apparatuses that can just like lose coherence, right? I mean, because like this is like the processing through quantum processes, like anything can just like turn them off and basically like make that like make it that all the information is being lost, right? I mean, so it requires like obviously like hardware research. It also requires like a better understanding of like what happens when qubits decohere, right? I mean, so there's this whole field of quantum error correction, which is basically like and then actually like a place where AI has a huge impact to be had, right? I mean, basically like try to predict when errors happen in the processing of information by those computers, right? I mean, so obviously it's very research heavy,
So,
but
so,
like,
so in
yeah.
the lab, I guess use cases that you've heard of.
Mm-hmm.
So you mentioned, I mean, the ones that are always mentioned are in the areas of cryptography and breaking cryptography.
Mm-hmm. Yeah.
And then you used the word inference.
Mm-hmm.
So what are some of the use cases on the inference
Yeah, no,
side?
absolutely. No, so I mean, so you're right with cryptography, right? I mean, cryptography though is not a machine learning use case, right? I mean, so
Yeah.
basically, like, so for me, like the pure machine learning use cases are like again things that require like massive amount of inference with like like at very high speed. So recommendation system, for example, like there is like very tangible like a use case of like transforming like recommendation models into quantum machine learning algorithms that perform the same operations on quantum computers, right? I mean, so basically, like this is a very tangible, non-generative AI yet, right? I mean, use case.
So
The other, yeah.
the recommendation example that
Mhm.
you saw, is it trivial or is it kind of realistic?
It is realistic, right? I mean,
Okay.
so basically, so then like it's happening, it's being tested now in production settings, but the challenge now is like basically like really truly seeing like the quantum advantage from it, right? I mean, so basically like I think we're reaching the point where for this niche applications, quantum is basically meeting the same like performance for inference as what you would see for regular computers, classical computers. But I think like now, like once we figure out like how to make this work, like it's going to be like a matter of like. So I was just gonna say like the other use case that I see like emerging as well is pharmaceutical applications, right? I mean, so precision medicine, because like you're dealing with like processes where you have like a not necessarily a lot of data, but like a very huge like dimensionality of the problem, right? I mean, and so I think like these are the two ones that are very tangibly like accessible through quantum computing in the next couple of years.
So let's table the whole deploying to production and the data stack you need to make this work in production. But right now, for those two examples, I guess recommendations and pharma, um, I guess the question is it justified to continue down the quantum path? In other words, are there signs that it's worth going down this path, that there will be a significant benefit to going down this path?
Absolutely. So you're like so what I see is like so there is a reason why pharma companies and financial companies like because there's a huge use case also for like like anomaly detection, so specifically like fraudulent activity on credit cards or whatnot, right? I mean, so I think like companies like large financial organization have a reason why they wouldn't want to go there. There is a reason why they're investing in like something that's still a very expensive technology, right? I mean, and so the reason is that they see the limits in classical inference, right? I mean, so basically, I was talking about the quantum advantage earlier and quantum supremacy. There is like we are facing like compute limitations for inference in those use cases I mentioned, right? So and like the executives in those companies that are testing out those new technologies are doing it like like they're not stupid, like they know why they're putting the money to actually like explore this new path, right? And so I think like going back to qubits, right? Right now, like the most powerful computers, quantum computers, like have like 100 qubits. This is about like the scale of like a computer like Willow, right? There are startups, for example, PsiQuantum, which is like one of the next generation quantum companies out there. They are trying to target like computers with 1,000 qubits in the next couple of years, right? And so because of the nature of qubits, like the benefit you get is exponential, right? I mean, so basically like when you get like a computer that has like 10 times more qubits, like you have exponentially more compute coming out of this, right? I mean, so I think those companies are doing this because they want to be ready for as computers become more and more, quantum computers become more and more powerful.
So just to clarify, so when you say these executives are seeing the limits of the traditional uh, computational technology, and quantum provides a way to overcome those limits. So what are the limits? Lack of compute. So is it scaling or what's the
Speed, it's
speed?
scaling, it's all of the above, right? I mean, it's scaling, like amount of data that can be processed, right? What quantum technologies are extremely good at is like exploring multiple paths at the same time, thanks to the principle of superimposition, right? I mean, so basically, like because like you can basically like explore many different paths where classical technologies, classical hardware, basically like would require like basically like distributed processes in order to explore like multiple different like so for pharma, for example, when you look for like new medication or medication that's specifically tailored for a single human being, right? I mean, you cannot like spend like days or months of compute just to tailor something specific to that person, right? So it's like it's all of the above, right? Cost right now is prohibitive for obvious reasons, right? And because there are few computers out there, but I think like once we start cracking like what it takes to basically like build a quantum computer with like hundreds of qubits, if not thousands, like I think like the potential becomes unlimited.
So again, so let's postpone the data ops for a second here.
Hmm.
But even in those lab experiments of recommendations and other use cases, what does the what does the quantum stack look like today, right? So I mean,
Yeah.
what's the equivalent of servers and
Yeah.
GPUs, and so do you have, because I'm assuming the cooling is insane, right?
Yeah. So it's like you would assume cooling is insane. It is. So basically, like, so when we speak about quantum computers, we're actually speaking about different technologies, right? I mean, there are many different ways you can produce a qubit, right? I mean, so basically, like, you have like the trapped ion technology, you have like photonics, right? I mean, basically, like you have like superconducting computers, right? And they all require different things, right? I mean, so for example, like superconduction, for example, requires going to like a extremely cold temperature. So yes, the cooling would be completely insane, right? I mean, requires like computers that are equally as complicated as particle detectors, right? I mean, which also need to be like close to like a 0 Kelvin in temperature. But there are an increasing number of technologies as well, which can be operated at room temperature, right? I mean, so when I say room temperature, it's better if you cool it off a little bit more. It's better because you reduce the number of like potential collisions that can impact those qubits and cause like decoherence. So you're actually increasing like coherence time and how stable the computers are if it's cooler, but it's not an absolute requirement from the existence of the computer per se, right? I mean, so I think we are getting to the point where there will be technologies that don't require cooling, right? However, like basically they're still like very very sensitive kind of machines, right? Then you asked the other question, which is basically like, what is the stack today? So I think this is the important question for me because like I've built my career around MLOps, right? I mean, and basically like I was among the first people to realize that the reason, like my strong belief is that like, you know, like I'll take the example of transformers just to speak like AI a little bit, right? The transformer technology was published for the first time in 2013, right? So and the first time you actually saw like a GPT application was basically like 10 years later, right? I mean, so it took 10 years to go from a paper into something that's in production, right? And really truly useful, right? So there are multiple reasons why it took so long. Like I think one of the reasons is like availability of the data. Like you know, like I spoke about that many times. Like ImageNet being like an unblocker for, you know, like image. Like you have the equivalent for language as well, right? Infrastructure, obviously, but I think like one of the big missing piece which we failed to see for the longest time is basically like the creation of like standardized software, like pieces of infrastructure, software infrastructure that would actually enable this, right? So until you had like airflow that was like, you know, like accessible for everybody to like create like data pipelines which are reproducible, which are shareable, like Kubernetes, like Docker, I think like was critical to basically like provide everything, right? With quantum computers, none of this exists. So basically like when you're talking about like partnerships between like an organization that wants to use quantum computers and quantum computing companies, it's basically like it's very manual, right? I mean, it's basically like how you could imagine like data science like in its early days where you
And,
had to
and
have a lot of back and forth.
and also, like you said, there's still some fragmentation. There's different groups approaching it from different ways. So
Yeah,
how can
yeah,
you build a coherent stack
yeah,
that
100%.
that holds across? So actually, before I'm really, of course, my goal in having you here is to talk about the data ops. But there's one thing that I don't really understand in this field, but I read a lot about, which is the stuff that Mike Friedman and Station Q down in Santa Barbara are doing, kind of this topological approach.
Yeah,
So, and
yeah.
then it's under Microsoft. So I think last year or something, they had a press release saying they had some sort of breakthrough from that group. So where does the topological approach fall? And I hear mixed. When they made that announcement, there was some pushback from other groups, right? So
Yeah.
what's
Well, I
real
mean,
there? What?
there is always pushback. So basically, maybe let me start by saying this, right? Topology is very in like quantum, right? I mean, so basically, like it's important for different reasons, right? I mean, so one piece of it is that uh, people have to understand that quantum computers are a different beast compared to regular computers, because when you mount a circuit in order, like basically like when you create like a, you know, like a, some logical thinking for like, or an algorithm to process data, in the classical case, basically like you use gates and you use the same hardware, right? For quantum computers, you need like basically like part of the logic lives in the circuit itself, right? I mean, so basically like, so you actually have to like physically modify how the qubits like talk to each other and are connected to each other. So the topology of the system itself is meaningful in the context of what you're trying to do, right? I mean, so basically like, so research in topology matters even to make quantum computers better and make quantum computers like specifically stronger. Now, since we're talking about topology, right? I mean, so basically like in order to like bridge to data ops, right? I mean, now quantum data ops, right? I mean, so basically, like I
No, no. I
have,
mean, I
yeah,
guess my
yeah,
point is there's a
yeah,
whole group
yeah,
under
yeah,
Microsoft
yeah, yeah, yeah,
that their bet is on this
yeah,
direction, right?
yeah, yeah.
And
No,
so
100%, right? I mean,
I
so
want to
yeah.
get a sense of how do they stack up to the other groups?
I mean, it's like it, you know, like it's early stage, right? I mean, so I think what they're working on is very interesting. It doesn't mean that it's necessarily the only
Yeah.
direction, right? I mean, but basically, like it's they won't be a single technology, anyways, right? I mean, so going back to what I said earlier, it's like it's even like what you look at the history of the CPU, right? I mean, and basically, like even the GPUs, you have like at a high level, it functions the same, but basically, like you have different ways of implementing. You have like different like mini architectures and whatnot, right? I mean, basically, like when we went in this direction, everybody adopted like silicon, right? In this case, it's even worse because you have so many different ways. So, like, you know, like we're talking about particle physics. So you have different types of particles that can support like transfer of information and basically
No, no.
implementation of
I
qubits,
just
right?
read a book
Yeah,
about
yeah, yeah,
NVIDIA and Jensen,
yeah,
a new book that came out,
yeah,
and I forgot that there were so many GPU startups.
yeah,
They just happened to be the sole survivor. But
yeah,
even in the GPU
yeah,
space, there were numerous people
yeah,
trying to
yeah,
address that problem, right? So,
yeah, yeah.
and obviously that's going to happen
Yeah,
here too.
but I
So,
mean, it's actually like building on that, right? I mean, I think it's interesting as well because like you know, like Jensen started Nvidia as a gaming company,
yeah.
right? I mean, so basically, like, so I think it was almost like coincidental that basically like they created like hardware to support like fast inference for gaming, right? I mean, and for like graphic units, right? And I think it's gonna be the same story here, right? I mean, which one is going to survive? It's not necessarily gonna be the best technology. It might be, you know, like a technology that has the right compromise between like cost and feasibility, like basically like getting the right funding at the right time, right? I mean, so it's very difficult to know, right? I'm just like basically glad there are different people like exploring different technologies, but it's still early, obviously.
All right. So on the data ops side, right? So I've read a bunch of your posts, which I recommend to our listeners, which you can find at quantumofdata.com. And I guess I never thought of data ops in this context
Yeah.
because I'm not paying attention. I always think it's 10 to 15 years away, right? But then you're bringing up, right? So if we get to the point where we get serious and we have to productionize some of these things,
Yeah.
well, obviously data ops will be a consideration, and then you start listing out some of these challenges, right? So first, quantum data cannot be copied or backed up.
Mm.
And
Yeah.
then results are probabilistic, which is something we're used to in machine learning, but then there's entanglement and
Yeah.
other things. So give us your checklist of challenges first, and then your checklist of early solutions to
Yeah.
these challenges, right?
I'm afraid there are more like challenges than solutions at this
Yeah.
point, but I mean there are a couple
Yeah,
of
yeah,
ideas,
and
right?
one of the reasons I think you wrote this series of posts
Yeah,
is
yeah.
you're concerned that no one is actually
No,
thinking
100%. Yeah.
about this, right? So,
Yeah. No, so you mentioned the main obvious one, but like basically like, so I would like to, you know, like talk about this and then we can go back to like topology. I think those are two different important problems related to quantum data ops, right? So let's start with like the concept we call like the no cloning theorem in quantum computing, right? I mean, so basically what this says, it's based on the same paradox as Schrödinger Kruger's cat, right? I mean, so everybody knows like basically like the concept of like you have a cat which is like you don't know if the cat is alive or dead. It's in the box. What quantum theory says is like as long as it's in the box, it's in neither one of those states. It's in superposition of both states, right? I mean, so basically like this is like, so when you think about a qubit, it's the same thing. It's like you don't know if it's 0 or 1 because it's a superposition of both, right? It's not even, people need to understand, it's not even just like the probability that one of these outcomes happen. It's actually both, like like a superposition of both, right? And then when you open, so the opening of the box is the representation of the measurement or the observation, right? I mean, so basically when you look at it, then it falls or it collapses into one of those states, right? I mean, based on, like, you can compute the probability based on the original state, right? But once you observe, the state disappears, right? I mean, so basically like you kill the information that used to live in the qubit at the moment you look at it, right? So basically like this brings like a paradox where if you could copy the information that exists in one qubit, then it would require looking at it and it would basically like collapse the information, right? I mean, so basically like this leads to like, and something insane to think about like in regular data ops, but like you can never copy like the information of a random state. You can only copy the information after it has folded, right? And so
So
it means like
that
yeah.
kills lineage and
Yes,
reproducibility right
exactly,
there.
exactly. It kills everything. It kills like checking.
Yeah,
It kills
yeah,
like
yeah.
basically like debugging, right? And because like when you debug, you actually
Yeah.
rerun the same program multiple times and see what's wrong. But like here in this case, something can go wrong, but then when you rerun it, it runs okay because something else happens even with the same original state, even if you can reproduce the same original state, right? I mean, so it's basically like so that's the sort of thing you have to think about, right? I mean, so you're absolutely right. Like it breaks lineage. It's like even if you were to train, like it goes beyond the data. It's like even if you could train an entire machine learning model, those machine learning models in classical machine learning are weights, right? I mean, so the weights themselves that you train are data, and then it means like once it's here, you cannot copy it, right? I mean, basically, like you wouldn't be able to distribute that model like the way you think about it, like in classical machine learning, right? So what you can do, however, is basically like rerun the process as you go, right? I mean, so basically, like it's a completely different way of operationalizing.
So you have the data. Obviously, a model is also data, right? So think about a recommendation engine. It's a
Mm-hmm.
model which has parameters.
Yeah.
So I assume then the model itself is subject to the same problems as the data in terms of you cannot
Yeah. Yeah.
you cannot
Absolutely. Which is
copy the
exactly
model. Yeah.
that. Yeah. No, I mean, so which is exactly why, like right now, we spoke about the recommendation use case, right? I mean,
Yeah.
the recommendation use case is like it's a case where the model is not very complicated. It's just like very personalized, right? I mean, basically like the computations that need to happen in order for you to receive like a valid like recommendation is not. It's more like based on like reading the data from somewhere, transforming it, and outputting something, right? I mean, so you don't need to remember basically like what was recommended. You just need to remember like the original status of like things you looked at or whatnot, right? I mean, so which also leads me to another important point. You still need to have that information somewhere. So I think like it's clear, and it should be clear to everybody, that quantum computers are not going to replace classical computers. There's going to be like some sort of hybrid, right?
Yeah.
Quantum computers are very fast to transform information, but they suck at remembering things, right? I mean, basically that's the way, like you have to think about this as like very short-term memory, right? I mean, so like this is sort of the challenge to like adopt like quantum computing for like attention or memory based kind of models like generative AI, right? I mean, that requires like embedded
And
memory, like
the use cases that you've discussed so far involve structured data, right? So
mm-hmm. Yeah,
structured data are stored in tabular format, right?
yeah,
So or maybe if you go into the more lake housey world, you got Parquet
yeah,
and all these
yeah.
things. But now you have quantum data, which in quantum mechanics, that's like now you have quantum mechanics. So is that now we're talking about Hilbert spaces, right?
Mm-hmm. Mm-hmm. Yeah.
So what's the storage?
Yeah.
What's the storage mechanism now?
No, exactly, right. I mean, so that's why I mentioned like the hybrid sort of use case, right? I mean, so this is where we touch on like the limits of what exists right now for quantum computing. There is active research on understanding basically the concept of quantum embeddings, right? I mean, which is basically like how do you transform classical information into something that is ingestible into a quantum computer, right? So it's really cutting edge, right? I mean, basically, like again, like I want to emphasize, like in my opinion, like basically, like we need to, yeah, no, so what I was saying is basically like so. I believe that, you know, like we've nailed for like how to process data and store data, manage data for the classical use case, right? I mean, so I think like at least for the foreseeable future, I don't see how. No, so when we talk about like storing data, right? I mean, so I think we've spent many years like in industry and in research figuring out like what data management actually means, right? And there is no clear benefit anyways to storing data with quantum yet, right? I mean, so basically, like I think like where I might come back to this is basically like the point where we have like smarter ways to benefit, like you were talking about like superposition of states or whatnot, right? Right now, like we're still like doing like a data loading like in quantum computers, like in a way that's very basic. Like basically, like you insert like one piece of information by qubit, which is not optimal, and you're not actually taking advantage of like the superimposition of or the you know like basically like a coordination between different qubits, right? So I think we're gonna be doing like a hybrid data management for a while, but there is an increasing number of people researching like quantum embeddings, right? I mean, so quantum embeddings is like basically like how you abstract away from classical data, classical bits, like basically like into something that's understandable for quantum computers, which is basically what I said, like how do you actually like load data in you know like basically like a entangled state. And basically like, because like the idea is like if you have 100 qubits, you would like to store more than 100 features by benefiting from, you know, like the interdependence of the different qubits, right? I mean, so but today it's true, it's still relatively early, right? I mean,
So, but as you mentioned, quantum computers are great at computing but suck at remembering.
mhm.
So maybe the right way to think of it is exactly that. You just
Yeah,
use it as a calculator
yeah, 100%. Yeah,
and then throw it away
yeah,
and
yeah,
then use
yeah.
and then call it again, right? So
Yeah. So I will like this is where we can start nerding out. Like I'll share like basically like I'll try to push like that thinking a little bit more. So yes, as long as we consider modeling the way we think about modeling for classical machine learning, right? I mean, so basically let me explain here. So about 2 years ago, I posted a post on LinkedIn that went viral where I was challenging how we do modeling for machine learning. I'm a physicist, right? So for me, when I think about models, I think about like the standard model of particle physics, right? I mean, so basically like the theory that's trying to like summarize like all of the interactions between particles, right? Because this is what I used to work on. And so in the context of physics, when you model things, you're trying to like explain the process that generates data, right? I mean, so basically, like, so if you capture basically like the speeds and locations of data, their masses or whatnot, you want to build a model that can basically explain why those particles have a specific speed or a specific mass at a specific point in time, right? What you do in machine learning is basically like it's not really a model, it's an extrapolation, right? I mean, it's basically points which are distributed in space, but you're never trying to actually model the process that like you're trying to like extrapolate, right? I mean, so basically it's a very different approach, right? And so this matters because in physics and because like quantum is a physical process, like basically like I think it's the right way of thinking about this, right? You're trying to like like go back to the original process that generates the data instead of like just like extrapolating from a like number of examples or samples, which is what you do like even for LLMs, right? And so there are like you have to think like basically what you have to think about is like you're not working with data sets anymore, you're working with data manifolds. So basically data manifolds is like the shape the data has like in the space it's trying to represent, right? I mean, and so basically like we were talking about topology earlier, but like I think this is very important because like I happen to be working for a company called ISD like about 10 years ago, which
Oh,
was like a
really? Yeah,
pioneer
yeah,
in
yeah.
the space of topological data analysis,
With Gunnar
TDA, right?
Carlson, huh?
With Gunnar Carlson, yeah,
Yeah, yeah, yeah, yeah, yeah.
yeah, yeah.
Yeah, yeah.
So basically, like,
I think,
at that time, so we can redo like if it's like
yeah, yeah.
at least it's a
So Gunnar
rehearsal.
Carlson and Ayasti, I think they, as best I can tell, the main use case was around clustering, right?
The use case, like the technique is like clustering, right? I mean,
Yeah,
so
yeah.
basically, like, so what his vision was basically like data sets have shape in space, right? I
Yeah.
mean, now basically like the underlying space it's trying to represent, right? So when you have a like point cloud, like like basically like clouds of points that are like as dense as you want, you have to imagine like basically where does it belong to? It belongs to like this complex manifold or whatnot, right? So TDA is a clustering-like kind of technology that tries to represent the topological, like abstraction of that shape of the data, right? And so back in the days, like because like that was long before quantum, it was a beautiful theory, but it wasn't necessarily useful in application, right? I mean,
Right.
because you could get away with like loading examples and using that in training a typical machine learning model, right? Because what topological data analysis does is like it models the data without the need for a model, right? I mean, it like intrinsically tries to represent the underlying process that is the reason why data is distributed in a specific way, right? And so I think like now this might be the time where like TDA actually has a real application because like that's the right way of thinking about things. Because like if you can abstract basically like convert and where it gets even more beautiful is like TDA did not catch on like as an industry application because it was extremely computationally expensive because it requires very complex computations, which like the hardware until now was not capable of supporting, right? So with quantum computers, right? I mean, basically, you would get that sort of acceleration even with the quantum computers of today, right? In order to like represent data sets into manifolds and then use those manifolds as the original distribution that you can sample from or generate data from, because like basically like there is actually a huge application in by quantum computers for synthetic data generation as long as you have like a tangible, viable distribution for that data. So I think this might be like the nut to crack, like in the context of data quantum data apps.
So I'm listening to this conversation. I'm a CTO for a large company, right? So I'm trying to understand AI and generative AI and what we should be doing there. Um, and and so on the other hand, there's this quantum computing, right? So I'm barely getting my head around AI and getting that in production. So how should I think about quantum computing? Is this something that I just don't think about for another 5 years, or?
No, I No, so I would say you don't, as a CTO, like this is gonna be like that. That's the beautiful part. I think quantum computers eventually will reach the point where they accelerate or enable the creation of applications and models for AI that even like traditional like infrastructure cannot support, right? Like I don't think it changes anything for the people in the application layer, right? I mean, basically, like all they need to know, like if you are a CTO, all you need to know is like there is better technology that's going to make like AI faster and more viable, right? I mean, basically, but where I think there is a huge problem right now is like the friction between both because you have very few like basically like look people like me who understand both are like not that common, right? I mean because like most people in AI tend to be with coming with a computer science background, right? And for me the friction is like basically like you mentioned earlier like the stack that's available. There is no OS for quantum computers. which means like there's no internet for quantum computers, right? I mean, it's almost impossible to have like different quantum computers like plugged to each other. There is one use case like in a, you know, like a research team like in academia, right? I mean, that basically like created like an early version of this, but it's not accessible, right? And everything else we talked about before, like all of the MLOps pieces, like what is like a containerization, what is like a, you know, like everything debugging, right? I mean, for quantum computers, this needs to be built, and I think it needs to be built now because otherwise, like basically, we're not going to benefit from this, right? I mean, and so I happen to be among the people who are worried about the negative impact of quantum because right now, when people talk about quantum, they are more worried about like the implications for cryptography and like basically like attacks and whatnot than they are about the benefits of it, right? I mean, so basically, I want to see the benefits before seeing like seeing the risks, like basically like change the way we live today. Right?
By the way, on the cryptography side, a lot of people have already deployed post-quantum cryptographic
Mm-hmm.
schemes anyway, right? And the other
Yeah,
question I have for you is,
it's
why should we worry about this stuff now if where we're at quantum computing is we're still in the equivalent of John von Neumann's computer, So the internet happened 50
no,
years
I mean.
later, right? You know the
Well, I mean, so you might be right.
Yeah,
What look, so okay, so what I'm seeing, right, is
yeah,
China is investing in quantum, right? I mean, so basically, like, look, for me, it's like if this technology becomes accessible to a small number of people and that small number of people has bad intentions, right? I
yeah.
mean, basically, like, this is a disaster. Like, basically, this is what people refer to as like Q-day. Q-day is like the point where you have this like a, you know, like a singularity in quantum where suddenly all of the data becomes accessible to everybody on the internet. All of your chats, conversations, like bank accounts become like publicly available to everybody, right? So I think it's important for countries to basically like mitigate that risk by also showing leadership in this space, right? I mean, beyond like basically like I was talking about the risk earlier, I think you cannot just sit here and like because like this is an important technology to develop, right? I mean, basically like it's important that the technology matures with like multiple. I'm actually very happy that there are many different ways of doing quantum computers because it means there are many companies. It means that you're not dealing with like a one rogue agent basically like trying to enable quantum while nobody else has an idea it's coming here. But it's just like AI, right? I mean, so I like one of the things, so I'll share something with you, right? I mean, so I've worked basically like in mitigating risks for AI. Like my job at DeepMind was related to data governance in particular, right? And I mean, I'm always like, you know, like really worried about like what happens if you use like sensitive data in a model that shouldn't see that data, for example, right? And I think there are too few people like AI can be an extremely dangerous technology for a variety of different reasons, right? I mean, so basically, like I don't need to explain all of them because it's all over the internet anyways, right? But basically, like so, I think like one of the things that makes me feel better about AI is that if you compare to the risks of nuclear technology, basically like 50 years ago or like you know like even a little bit longer than that, right, is that you couldn't build a nuclear bomb in your backyard because it's expensive, it's difficult to get like the right like you know like the right minerals in order to get there, and it's controlled, right? I mean, basically like governments are spying and measuring like quantum or nuclear activity, right? With AI, it's basically like I was always worried that because you have open source, right, you can have anyone build anything with AI, including bad stuff, right? I mean, so basically, like, so in a way, it's a lot more dangerous. But because infrastructure is difficult to access as well, you still have a gatekeeper in, you know, like basically like who's using those computers and whatnot, right? I mean, basically like so it's a sort of form of mitigation. I also believe that the open source itself is actually a mitigation because you put progress in AI in the hands of everybody, right? I mean, as opposed to having like just one age and the rest of the world, right? We need to think about what this means for quantum computing, right? I mean, basically, like there needs to be sufficiently enough people involved to think about the risks, to mitigate the risks, to discuss regulations, and to basically like you know like make sure that we're fairly competing with, like other countries and
So in
other.
Jennifer, in AI, there's basically two superpowers, right? US and China. What's the
Yeah.
geopolitical landscape for quantum?
I mean, I think it's about the same, right? I mean, basically, like I see a lot of progress, like in quant, like every now and then when you follow like quantum news, like basically like you have like massive investments in quantum computers or quantum computing centers, like in China, right? I mean, so basically, like I think like the same needs to. I mean, for example, something I don't see clearly in the US just yet is like you mentioned those like lots of companies, most of them still early stage. You have a couple of public companies that are already out there. But there needs to be like a clearer like governmental level initiatives for this, right? I mean, so basically like the fact that those companies are doing partnerships with the DoD, with NASA and whatnot, like basically is enabling this. But I think uh, there should be like clearer initiatives at the government level to fund research in quantum computing, right? I mean, in a way that I don't see happening right now.
So for listeners who, are coming from data engineering, ML, data science background, right? So they're listening to this episode, they say, okay, I've got the skills in this side. I can help build the data stack, the data ops stack for quantum, but I know nothing about quantum. So
Mm.
how do I level up on quantum?
It's not trivial. So basically, like, so I would say like that's a gap I'm trying to solve like those days because like you're absolutely right. I think like so quantum computing is interesting because it's a system-oriented way of thinking, right? I mean, basically like you're thinking about like superposition of states or whatnot, right? Whereas classical computing is like succession of like sequences of facts and execution, right? I mean, so it's a completely different way of thinking, right? But it's not as hard to learn as people imagine, but it's a different way, right? I mean, so it's not something you can just like, it's not like C++ and it's easy to learn Python, right? I mean, basically, like you have to rethink, like basically, like what it means to build a model, right? So I think there is like material missing here when I look at like what exists, like quantum computing books are first like focused on hardware and they're targeted at physicists, right? I mean, so they assume you already know the math or whatnot, right? At the same time, the math is, like it's not as hard, right? I mean, basically, like it's like if you know like a linear algebra because you've done like machine learning, I think it's relatively easy to extrapolate to quantum. You just need to have the right like courses out there. So basically, like I think it's also important that universities start like giving, like or providing like quantum machine learning classes, right? I mean, and basically like an idea of like how to
Is
bridge both,
is
right?
anyone doing this?
I mean,
In
that's one of the things I'm trying to do, right? I mean, basically, like, trying to like bridge both. Like, I'm like working on a book on the topic as well, right? I mean, but
have
basically,
you
like,
have you
I
seen
think I think there's still like a
have you seen a quantum machine learning class in any university in the US?
I don't see any on Coursera. I see a few basically like introduction to quantum computing, like snippets or classes on YouTube, but it's not as formal as I see other spaces be. And I would encourage people who have my background, like basically like in quantum slash like AI to basically try to bridge that gap.
So you believe that a data engineer doesn't have to go back to school and take a bunch of quantum
No,
mechanics classes and
it's a
in
use.
order to
Yeah.
contribute?
Yeah. No, I think it's just like, like it's just the same way that basically like, like when we made the shift of classical like machine learning algorithms to generative AI, the algorithms, I
Or I
think
guess
there's a little bit
Jennifer,
yeah.
there was a period in time when a bunch of people in data engineering got interested in genomics and biotech, and then they
Yeah.
just went in and they became productive.
Yeah.
They,
Yeah.
I don't think they went to grad school.
No, absolutely not.
They just
No, and
learned.
like,
Yeah.
and it's the difference here, though. I would say, like, basically, like, so you can, like, again, it's math, right? I mean,
Yeah.
so basically, like, if you understand the math, you understand like a matrix calculus, you understand like tensorial, like properties of like calculations and whatnot, right? I mean, I don't think it's that difficult, but you need to have an understanding of the framing, right? I mean, so and yeah, I mean, I don't think you need to go back to school, right? The difference here is like basically I would say it's more fundamental in the context of like like you're talking talking about genomics. Genomics is an application, or it's a space where you want to apply machine learning. In this case, it's like rethinking how. So basically, it's more fundamental. So it's probably worth like going a little bit more in depth. But I don't think the math is as violently different as everybody can imagine.
I think what will happen, if I were to predict, is there has to be one clear example where someone used quantum machine learning, reaped so much benefits, and then people get get so excited, and then suddenly universities have how all these universities have data science institutes and programs now. So there has to be some sort of
application
moment, like ImageNet or
100%.
something
No,
like that,
and
right?
so you're absolutely right. The challenge I see though is basically like, so because the hardware is still being developed and because it's so like, like scarce, right? I mean, because like it's so difficult to have like stable computers. You have a few of those computers on the planet, right? I mean, so it's not made like available or accessible that easily to the masses, right? I mean, so basically you mentioned like the ImageNet like moment, right? I mean, ImageNet moment was like, we distribute the data so that people are not blocked by a lack of data. I think the equivalent here is like basically like is there like, this is maybe where governments need to jump in and basically say like, we're making like n number of quantum computers available for research. Like based on like proposals and whatnot, right? Because most of those computers are still owned like by private companies, it's not as easy. Right?
But I guess by ImageNet moment, I mean you have an existing thing, in that case, an existing competition, and then the deep learning guys learned how to program GPUs, and they blew people away. So it's almost like you have some existing use case or workload, and then the quantum machine learning guys or gals come in and just shock the world, right? So
No, I think it will happen. I think like there are a couple of like elements that are still missing, right? I mean, the ones we discussed with like availability of like the first and foremost, like basically like, so you can have the exact immediate moment because like you cannot make data accessible. You would need to rethink what data means, like if it's a
or
manifold or
some
whatnot, right?
existing problem where they go in and
Sure. Yeah.
and blow the existing.
No, you can take the example of autonomous driving, right? I mean, this is how like we cracked like a lot of like the challenges in AI as well. So
Yeah. And with that, I guess just go to quantumofdata.com, and what other resources would you want to point them to?
no, I think that's good. I publish a lot of things on LinkedIn, so you can follow me on LinkedIn as well.
Yeah. Thank you, Jennifer.